Welcome to you all to this MOOCs online video course Theory of Yarn Structure. In the last lecture we started with module 6 radial migration of fibers in yarns. We have covered about general fiber path in yarn, how to characterize this, then we talked about fiber element, then we talked about some angles to define fiber path in yarn, then we discussed about Taylor's ideal fiber migration model, and at the end we observed that Taylor's ideal fiber migration model is not able to explain experimental results of radial migration of fibers in yarn. So, we start from there in this lecture. So, the obvious question is that why Taylor's ideal fiber migration model does not explain the experimental results of migration. We observe totally different trends. So, we wish to critically examine the assumptions of Taylor's ideal migration model. If you remember, the first assumption was related to definition of radial migration, which is no doubt valid. Second assumption of Taylor's model was packing density constant at all places inside the yarn. This assumption, although we know it is not experimentally fully correct, however, this is an idealized situation. So, we can to some extent agree to this. Third assumption was the absolute value of this is same for all fibers present at radius r. This assumption is idealized and is acceptable. The fourth assumption was nu r is constant. Nu r, if you remember, it is the number of fiber segments intersecting a cylinder at radius r per fiber per unit length of yarn. This assumption is probably not correct. Why do we feel so? We feel so because if we imagine the inside of a cylindrical yarn, then we see that at the core the volume of yarn is very less because radius is very less. So, fiber to fiber contact, fiber to fiber contact is very less there. At the same time, if we think about the surface of the yarn where packing density is very less, if the packing density is very less, then the fiber interaction is also very less. Therefore, we feel that this number of fiber segments intersecting a cylinder at any radius r per fiber per unit length of yarn is probably not constant, it varies. Here you see a cylindrical yarn near to this region, near to the core. In this region, the volume of the cylinder is very less because it is very close to center of the yarn. So, its radius is very small. So, fiber intersections must be small here. If we think about a cylindrical region near to the surface, say this region, near to this region, as we know, packing density of actual yarn is very less at the surface. So, the packing density is less, so fiber volume is also very less, number of fiber is very less. As a result, interaction among fibers must be less too. Somewhere inside the yarn, in between these two cylindrical surfaces, packing density is significant. So, number of fiber intersections must be very high somewhere near to this cylindrical region, because fiber number of fibers is too high here. So, fiber to fiber interaction, fiber to fiber contact, packing density, all are very high in this region. So, therefore, it is felt that the packing density in this region is high, fiber to fiber interaction is very high. As a result, it is thought that this nu r, number of fiber intersections, is not same at all places inside the yarn. Wherever fiber volume is too high, it is very high. So, assumption 4 is modified. So, in this model, assumption 4 is modified. What is this assumption 4? Assumption 4 is modified in this way: number of intersections, number of fiber to fiber interactions must be proportional to the fiber volume in a cylindrical region. So, what is fiber volume? What is the volume of the cylinder? 2 pi r into dr into zeta. This is the volume of the cylinder, and what is the fiber volume? Multiplied by packing density, because as you know, packing density is defined by the ratio of fiber volume to yarn volume. When the yarn volume is 2 pi r dr times delta zeta multiplied by packing density will give you the fiber volume. So, nu r is equal to capital C 2 pi dr delta zeta is proportional to 2 pi dr delta zeta into r into mu. If you look carefully, this quantity within the parenthesis is a constant. This is same for all ready. So, we can write nu r is a constant into r into mu, where C is a proportionality constant. Proportionality constant. So, this way we modify the fourth assumption of Taylor's model. So, we are now discussing a new theory which is known as model of equidistant radial migration of fibers in yarns. So, in this model assumption 4 is modified in this manner. Now, so it is evident that the model path of fibers, if we imagine, then in this model of equidistant fiber migration model, it starts somewhere here, then it has very less intersections near to the surface, maximum intersection fiber to fiber intersections happening over here, at the core also it is very less. However, if you remember Taylor's model, these fiber intersections was considered to be same at all places. So, in Taylor's model the path was assumed to be like this. Regular fiber path. But in this model fiber path is random. So, this is the basic difference between Taylor's model and model of equidistant radial migration. Now, if we look at what will be the value of period of migration, it is definitely varying in this model. This period of migration can be written by 2, because you remember nu r was defined by this. So, when small n is equal to 1, how many fibers or fiber segments will intersect the axis in order to get a period p? 2. So, is nu r by 2, right. So, we can write period is here now varying. Now, what was nu r? Nu r was capital C r into mu, right. We consider this 2 by capital C is a constant, because capital C is a constant, we can write it as a small c. So, we write small c into r into mu, right. So, nu r is equal to 2 by p, and p is equal to small c by r into mu. So, 2 r mu by small c. So, this is the expression for nu r. You see here, r, if r varies, nu r will vary, because c is a constant and mu is also assumed to be constant in this model too. So, this is how this model is different from Taylor's model. Now, we will go back to the fundamental equation of radial fiber migration. We will substitute nu r there, and we would like to see what is the expression comes out and what does that expression tells to us. So, if you remember the fundamental equation of radial fiber migration, mu nu r minus 1. This was the fundamental equation of radial fiber migration. Now, we substitute nu r this and tangent beta 2 pi r z. We will make these two substitutions into this expression, and we would like to see what it comes out. So, tan square beta, let us write as tan square beta here, we will substitute in the denominator mu nu r 2 r mu by small c into n s z square, tangent beta 2 pi r z square minus 1. So, what it becomes is 1 plus tan square beta mu into 2 pi r z into c 2 r mu n s z square minus 1, right. So, we would like to see what it comes out. numerator we do not change, denominator you would like to see what is coming out. These 2 and these 2 cancel out, this mu cancel out, this z cancel out, this r cancel out. So, we are left with a simple form pi into c n into s square minus 1. Pi is a constant, small c is a constant, n number of fibers in the cross section of yarn is constant, small s is fiber cross sectional area, that is also constant. So, pi c divided by n s is a constant. Let us assume this is equal to capital Q, which is a constant, then we write as Q square minus 1. This is a very important expression. This expression is known as fundamental equation of equidistant migration. So, the last expression is known as fundamental equation of equidistant migration. If we like to know how to find out Q, then we can do one thing. So, Q is equal to pi times small c by n into s. Now, what is n s? Number of fibers in the cross section of yarn multiplied by cross sectional area of one fiber. So, this is the cross sectional area of all fibers, substance cross sectional area S naught. What is S naught? S naught is capital T naught by rho is the starting fineness of parallel fiber bundle, which is equal to fineness of the yarn into 1 minus retraction. We discussed this in helical model of fibers in yarn. Now, we know yarn diameter square takes this form. So, T by rho is equal to pi mu capital D square by 4. If we substitute this here, then pi mu D square by 4 into rho 1 minus retraction, right. Then if we come back here in Q, so pi times small c pi mu D square by 4 into rho 1 minus retraction. What we see that this pi and pi will cancel out. So, sorry, this rho will not be here. So, we can write it further, small c by d by 2 square mu into 1 minus retraction. So, this is about capital Q. Okay. Now, we would like to derive the expression for fiber path at different radius. So, zeta versus small r. So, we go back to our fundamental equation of radial migration. Tan square alpha is equal to tan square beta plus 1 divided by q square minus 1. So, tan alpha will be equal to plus minus 1 plus tan square beta q square minus 1. So, what is tangent of alpha? Dr by d zeta from definition, dr by d zeta plus minus root over 1 plus tangent of beta is equal to 2 pi r times z, 2 pi r times z square divided by q square minus 1, right. So, we can write further dr by root over 1 plus 2 pi r z square is equal to plus minus d times zeta root over q square minus 1, right. So, if we integrate this plus minus this. So, we need to do this integration. Let us think about this part. So, integration dr by root over 1 plus 2 pi r into z square. How to integrate this? Let us assume two pi r into z is equal to x. So, integration by substitution. So, 2 pi z dr is equal to dx. So, integration dr is dx by 2 pi z and this is your x, no x square plus 1. So, 1 by 2 pi z is a constant, it can come out of the integral. This we write in a little different manner. Let us multiply by this in the numerator, we must do the same in the denominator also. Right. Now, we can further divide this by this quantity. So, what we will get is 1 plus by into dx. Now, we will consider this quantity as y. So, we rewrite the last step for our convenience. This is equal to 1 by 2 pi z integration 1 plus divided by 1 plus x squared plus x into dx. Assume root over 1 plus x squared plus x is equal to y. So, this is 2x by this plus 1 dx is equal to dy. So, 1 plus x by root over 1 plus x square into dx is equal to dy. So, then we can write 1 by 2 pi z, this is your dy and this is your y. So, integration dy by y is logarithmic y, 2 pi z ln into y. What is your y? Y is root over 1 plus x square minus x. What is your x? X was 2 pi r z, 1 plus 2 pi r z squared minus 2 pi r z, right. So, 1 by 2 pi z logarithmic of root over 1 plus 2 pi r z square plus, sorry, this must be plus 2 pi r z. So, this was one integration. What was the second one? Second one was simple one, d zeta by this. Now, here this is constant d zeta. So, root over q square minus 1 into zeta. Okay. So, what was our original form of integration? So, our original form of integration was this dr by root over 1 plus 2 pi r z square is equal to plus minus integration d zeta this. So, this integration we found as one by 2 pi z ln root over 1 plus 2 pi r z square plus 2 pi r z is equal to plus minus zeta by this plus say k, k is integral constant. right. So, we can rewrite it further 1 plus 2 pi r z square plus this is equal to plus minus 2 pi z root over minus 1 into zeta plus k. So, this expression will give you the fiber path inside the yarn. Now, if you put different values of r, then you will realize that this gives you a almost straight line. So, we can say that the infinitesimally small curve of a fiber follows almost a linear path inside the yarn. So, imaginatively inside the yarn it follows this kind of straight line. So, in the last expression if you put different values of r, then you can find out different values of zeta. If you plot them r versus zeta, you will obtain a curve which will be resembling very similar to this straight line. So, this infers that the path of infinitesimally small fiber segments inside a yarn is very near to a straight line. So, 1 plus 2 pi r z square plus 2 pi r z is equal to 2 pi z root over theta plus k. So, if you take different values of small r, you will get different values of zeta. If you plot, you will get such behavior. Now, we set this model as model of equidistant migration of fibers in yarn. Why we said so? So, why this model is called as equidistant migration of fibers in yarn? So, we would like to talk about it now. So, name of the model we will discuss now. If you remember, one point of time we derived this expression in fact, this expression we derived at the beginning of this module. Dr by dl is equal to tan alpha divided by square root of tan square alpha plus tan square beta plus 1. Now, what this model gives? This model gives us tan square alpha is equal to tan square beta plus 1 divided by q square minus 1, right. So, tan square beta plus 1 can be substituted as q square minus 1 tan square alpha. So, what we will get, dr by dl is equal to tan alpha square root of tan square alpha plus q square minus 1 tan square alpha. So, in the denominator tan square alpha, if we take, then what we see, 1 plus q squared minus 1. So, what we will get? We will get tan alpha by q tan alpha, right. So, dr by dl is equal to plus minus 1 by q, right. What does that mean? This means dl is plus minus q times dr. Look at this expression, dl is plus minus q times dr. dl is the change in length of fiber segment, dr change in radius, q is a constant. So, the fiber length increases equidistantly with steps of radius. The fiber length increases equidistantly with the steps of radius. That is why this model is called as equidistant migration model. That is why this model is called as equidistant migration. Now, we will consider some approximations. If you remember, in Taylor's model also we considered two approximations. One was slow migration, period of migration was very high, so slow migration. So, the factor k, capital K there was very high. Second assumption was tan square beta is much less than 1. In this case we will consider the same, that is tan square beta is much less than 1 is valid for all radii r. So, what will become? Tan square alpha tan square beta plus 1 q square minus 1, right. Now, if tan square beta is very small, then 1 plus a very small quantity is approximately 1. So, we can write it as 1 by q square minus 1. So, tangent of alpha will be plus minus 1 by root over q square minus 1. What is tangent of alpha? dr by d zeta 1 by root over q square minus 1. So, d root over q square minus 1 dr will be equal to d zeta. So, if we integrate this expression, what we will get? We will write here plus minus 1 into r is equal to zeta minus a small k is integral constant. Right. So, zeta is equal to plus minus root over q square minus into r plus k. Look at this expression. This is an equation of a cone. That means, the fiber path approximately follows conical inside yarn. So, how does it look like? Imaginatively, this is how the fiber path will look like. So, it starts from somewhere here, it touches the surface. So, this is how it touches, then again it goes inside, again it comes out, touches the surface, goes inside. So, this path resembles path of a cone. So, in equidistant radial migration, if we consider the approximation, then fiber path follows cone. Otherwise, we can say the fiber path inside a yarn approximately follows a cone. So, this is all about equidistant migration of fibers in yarn. Now, the very important question rises whether this model is able to explain the experimental results correctly. So, this is how is the comparison between theory and experimental results. Comparison, theory versus experiment. What we see that in this graph, along the x axis tangent beta 2 pi r times z is plotted, along the y axis absolute value of tangent alpha multiplied by tangent beta. So, this region is same in the comparison of Taylor's model. So, this is basically the experimental region, all experimental data fall in this region. Right. So, this is your experimental region. Now, two types of curves are there. One is original, second we see approximation. The original we have derived into tangent beta is equal to root over 1 plus tan square beta root over q square minus 1 into tangent beta. So, this was original fundamental equation. So, these continuous thick lines black color for different values of q we obtained. For example, q is equal to 7 here, show this line. So, this line is obtained from this expression, right. And also you see one approximation line is dotted line is this line for q is equal to 7. How we obtain this approximation line? Approximation line we obtained by tangent alpha into tangent beta is equal to tangent beta root over q square minus 1. So, if you substitute q is equal to 7 for different values of tangent beta, you will obtain this dotted curve. For q is equal to 10, you will obtain this dotted curve. For q is equal to 3, you obtain this dotted curve. 13. For q is equal to 13, you obtain this dotted curve. For q is equal to 16, you obtain the last one dotted curve. So, what is interesting to see here that the equidistant migration model shows a very good correspondence between theory and experiment. That means, by changing one assumption in Taylor's model, that was assumption 4, nu r is proportional to radius r, we can see that the derived model explains the experimental results satisfactorily. So, this was about the model of equidistant migration of radial fibers in yarn. Now, we will have one numerical exercise now. So, the numerical problem is set in this manner. A carded ring spun yarn of 36.8 tex count and 497 meter inverse twist was prepared from viscose fibers of 38 millimeter length and 3.5 decitex fineness. This yarn was characterized for the radial fiber migration in this yarn by tracer fiber technique, and we obtained the following results. For different value of smaller by half of yarn diameter 0.1, 0.2, 0.3, 0.4, 0.5, we measured different values of period of migration in millimeter 12, 6, 4, 3, 2.4. The values of packing density and coefficient Kn were found to be 0.536 and 0.93 respectively. Find out the fundamental equation of equidistant radial migration of fibers in this yarn. So, this is how is this problem. So, let us solve this problem. What is given is mu 0.536 and coefficient Kn is given 0.93. It was a also given yarn count capital T, .8 tex, twist is given 497 turns per meter. So, you have to first find out yarn diameter. as we know from yarn diameter, module 2. So, if we substitute the values here, 4 into 36.8, 3.14, 536, viscose fiber 1510 kg per meter cube is the density, right. So, this value we will obtain 2415 in millimeter. Let us consider it as 1500. Viscose fiber density 1.5 gram per cc. Then what is given here? In the table, this value is given 0.1, 0.2, 0.3, 0.4, 0.5, P is given 12, 6, 4, 3, 2.4. From there we can find out R, because we know now D. So, R is equal to, so R by D by 2 is equal to say 0.1. So, R is equal to 0.1 into D by 2, D is given here. So, if we do this, then we will find out 0.0121, 0.0242, 0.0363, 0.0484, 0.0605. Roughly we will find these values. Now, what was small c? R times P times mu in equidistant radial migration. We know R, we know P, we know mu. So, if we multiply these three, then we will get this value 0.0778. You will see that this value will be same in all other cases. Right. So, we obtain now this table. We have to now find out fundamental equation of equidistant migration. As we know, the fundamental equation is tan square beta plus 1 into q square minus 1, where q is pi times c by n into s. The value of c we obtained as 0.0778. We have to obtain values of small n, number of fibers in yarn cross section, and small s, that is fiber cross section area. How to find out small n? Small n is equal to coefficient Kn into yarn fineness by fiber fineness. The value of coefficient Kn is given here 0.93 into 36.8 tex divided by 0.35 tex. So, this value will be coming to 98. So, this is your 98 into small s. How to find out small s? Cross sectional area, we know this relation from module 1. So, this was 0.35 divided by 1500. So, this value will be equal to this. So, if we substitute 2.33 into 10 to the power minus 4, this will be coming is equal to 10.70. So, the fundamental equation becomes 10 square plus beta plus 1 10.7 square minus 1. So, this is the fundamental equation of radial fiber migration in this yarn. So, for different value of beta we can obtain different value of tan alpha from this example also. So, this completes the numerical problem in this module. Thank you very much for your attention.